From Launch Complex 41 at Cape Canaveral in Florida, this is Atlas Launch Control at T-minus 2 hours and holding. The countdown clock entered a planned 30-minute built-in hold approximately 6 minutes ago, and we're now just over 2.5 hours away from the liftoff of NASA's TDRS-L tracking and data relay satellite. Launches atop a United Launch Alliance Atlas V rocket from Complex 41 at Cape Canaveral. The launch window today extends from 9:05 to 9:45 p.m., a duration of 40 minutes. This will be the 43rd Atlas V launch. Of those, TDRS-L will be the 11th NASA mission to launch on an Atlas V rocket. We also just completed a weather briefing with Clay Flynn, our launch weather officer from the 45th Weather Squadron, and the conditions remain generally favorable, with just a 10% chance of not meeting our launch weather criteria. Currently at the launch pad, the temperature is 55 degrees, with winds from the north 5 to 8 knots. At lunchtime, the winds will be from the north 10 to 15 knots. The temperature will be 46 to 47 degrees, visibility 7 miles or greater, with scattered clouds. And right now there are no weather constraints toward a launch tonight, other than the possibility of some thick clouds from the north from an approaching front. Otherwise, good conditions for launch tonight. Looking aloft, no shears observed currently. The highest wind is at 45,000 feet and 105 knots. We're going to look now at some video of the rollout of the Atlas V rocket with the TDRS-L spacecraft, which occurred on yesterday morning at about 10:22 a.m. Atlas V has a 14-foot diameter fairing for this mission, and with that has an overall height of 192 feet for the rocket. The Atlas V liftoff weight will be 746,061 pounds. Of that, TDRS-L fully fueled for flight will be just over 7,600 pounds. The Atlas stage by itself is 106.5 feet long, 12.5 feet in diameter, burns liquid oxygen and RP-1 fuel, along with liquid oxygen. During our launch tonight, it'll burn just over 4 minutes before the Centaur stage fires. The Centaur is 41.5 feet long, 10 feet in diameter, burns liquid hydrogen and liquid oxygen. First burn of the Centaur will last 14 minutes and 12 seconds, and the second burn 1 minute 59 seconds. And at that point, the TDRS-L spacecraft will be ready for spacecraft separation. At this time, all of our launch preparations continue to go smoothly. We're still targeting a 9:05 p.m. liftoff tonight. At T-minus 2 hours and holding, this is Atlas Launch Control. This is Atlas Launch Control at T-minus 2 hours and holding. Our countdown continues to go smoothly, targeting a 9:05 p.m. launch. And joining us now here in the broadcast booth at the Atlas Space Flight Operations Center is Greg Williams from NASA headquarters. He is the Deputy Associate Administrator for Policy and Plans for Human Exploration. And Greg, would like to welcome you very much, and you can give us a little bit of discussion about the role that TDRS has played and is playing now and is going to play, because it's rather important for our future space exploration plans.
Yes, indeed.
Let's go ahead and roll that, and Greg, if you can kind of tell us what it is that we're seeing as we go along.
Sure. TDRS is part of our Space Communications Navigation Program. As you can see, from the early days of space exploration, the 50s, 60s, even into the 70s, we were totally reliant on ground stations to communicate with our Earth orbiting and deep space spacecraft. And while that was fine for the early things we wanted to accomplish, it really only gave us coverage about 10 or 20% of the time. And we really needed to get to a place where we could have continuous coverage to really guarantee that we can control a spacecraft, operate them safely, and return the data from the Earth. In the 80s, we began launching the TDRS spacecraft, and what that really gave us was line of sight continuously for the Earth orbiting spacecraft that you can see here. We control the International Space Station in terms of telemetry and commanding, and also receive data back down to the Earth from the space station, keep our crews safe and productive. Also, the Hubble Space Telescope, which is locking secrets of the farthest distance of the universe, communicates to the Earth through the TDRS space network and the ground station associated with it. Similar to the Earth observing satellites, for which we get so much data on climate change and weather and natural hazards prediction, comes again through the TDRS space network. And we're really seeing now is us being able to communicate through the TDRS antennas, that data streaming down in hundreds of megabits per second to the ground stations in Guam, which is then redistributed through White Sands. As we move into the future, where we really want to get to is laser communication. As you can see, we've already demonstrated laser comm from the LADEE spacecraft in orbit around the moon. What this allows us to do is be able to move away from, eventually, radio frequency dependence and into laser communication, where we can transmit enormous quantities of data from enormous distances in deep space. As you can imagine, a narrow laser beam acquiring a spacecraft at the distance of the moon or even farther is quite an exercise in pointing and acquisition. And yet we've been able to accomplish this and demonstrate we can with the laser comm demonstration on the LADEE spacecraft in orbit around the moon.
So how do we see the demand for the TDRS capability? There's obviously just tremendous quantities of data that have a requirement now to come back, and with Space Station and Hubble and now other spacecraft that have great data requirements, are we capable with enough spacecraft, TDRS spacecraft, to be able to handle even all that we've got coming in the near term?
Well, we are. TDRS allows us to do that. This is the third generation of TDRS satellites that is being launched. TDRS-K last year, TDRS-L this year. And these are going to give us that capability well into the mid-2020s. We have, as you indicated, enormous quantities of data coming back from Hubble Space Telescope, from the Earth observing satellites, from the space station, and TDRS really gives us continuous contact and communication with all of those assets.
Well, Greg, thank you very much, and we're looking forward to not just the launch tonight, but all of the capability that this is going to be giving us going forward, even in the near term. So thanks very much.
You're welcome.
And we're still at T-minus 2 hours and holding. We'll be coming out of the planned hold very shortly. This is Atlas Launch Control. This is Atlas Launch Control, T-minus 2 hours in holding. In preparation for coming out of this planned built-in hold, we'll be listening to our NASA Launch Director Tim Dunn polling his team for a readiness to come out of the hold. This is Atlas Launch Control.
And attention all stations, this is the NLM on the NLM net, ready to conduct the cryo tanking poll. Current status for today's launch attempt, we have a good vehicle, currently working, no issues. We have a clean range. We have good range instrumentation at this time, and we have a healthy spacecraft. So with that, I'd like to begin the cryo tanking poll with NASA CE.
NASA CE, go.
SMA.
SMAs, go.
SMD.
SMDs, go.
NASA MEM.
NASA MEM is go.
NAM.
NAM is ready.
NASA MEM is go.
NAM.
NAM is ready.
NLM copies. The NASA team is ready for TDRS-L cryo tanking.
This is Atlas Launch Control, T-minus 2 hours in holding. Standing by now for our launch conductor, Ed Kidda from United Launch Alliance, to conduct a pretest briefing for coming out of the planned built-in hold and going into our cryogenic tanking operations. Even the Atlas rocket being launched tonight with TDRS-L is going to be tracked by the TDRS system, beginning 14 minutes into flight after loss of signal from the Antigua tracking station in the Caribbean. 11 tracking and data relay satellites have been launched since the first one launched on the Space Shuttle on April 4th, 1983, 31 years ago. The TDRS system allows almost constant space communication now. Spacecraft was built for NASA by Boeing Satellite System. And right now we've been informed that all of our downrange tracking assets, which include the ones here at the Cape, the one down at Jupiter Inlet in South Florida, and the Antigua station are go, ready to support. And as we said, after Antigua, we'll be transitioning to the Tracking and Data Relay Satellite System. We'll be on TDRS East for a good portion of the flight of the vehicle and transitioning to the TDRS stationed over the Indian Ocean for the latter part and of the flight and spacecraft separation. At T-minus 2 hours in holding, this is Atlas Launch Control.
Pretest briefing. This operation is classified as hazardous. Cryogenics will be loaded, ordnance items are installed, and high pressure and inert gases are in use. Any anomaly will be brought to the attention of the launch conductor. Evaluation will be performed by a support team led by the anomaly chief and the vehicle system engineer on Channel 6. COM Channel 1 will be the primary command channel, with backup being COM Channel 2. The following documentation will be in use for today's operations. Test plan X45-LCCMD-SLC, plan revision 21. There are no order revisions. PSM document configuration AV-043, revision F. Readiness poll for cryogenic tanking. Atlas systems, propulsion.
Ready.
Hydraulics.
Ready.
Pneumatics.
Ready.
LO2.
Ready.
Water.
Ready.
Centaur systems, propulsion.
Ready.
Pneumatics.
Ready.
LO2.
Ready.
LH2.
Ready.
Has gas.
Ready.
Electrical systems, airborne.
Ready.
Ground.
Ready.
Facility.
Ready.
RFFTS.
Ready.
Flight control.
Ready.
Instrumentation.
Ready.
COM.
Ready.
Timer.
Ready.
GC cube.
Ready.
Umbilicals.
Ready.
ECS.
Ready.
Redline monitor.
Ready.
Quality.
Ready.
Ops safety manager.
Ready.
ULA safety officer.
Ready.
Range and weather.
Ready.
Launch director.
Ready.
Proceeding with the count. Verify count to start at 23:55 Zulu with a launch window interval of 02:05 to 02:45 Zulu.
Roger. Count will start at 23:55 Zulu. With a launch window of 0205 Zulu to 0245 Zulu. Go.
This is Atlas Launch Control, T-minus 2 hours and holding. We're less than 30 seconds away from picking up our countdown. We're still going to count in 10 seconds.
3, 2, 1, mark.
And we're now at T-minus 2 hours and counting.
Start Centaur bottle pressurization to flight level. Roger. Start Atlas AHP pressurization to flight level. Roger. Pressurize Atlas RP1 tank to step 2. Roger. Adjust CISA temp to 110 degrees Fahrenheit. Roger.
T-minus 1 hour, 59 minutes.
Initiate CEC safing purge. Roger. Start CEP to high flow. Roger. Start CFA purge in displacement mode. Roger.
This is Atlas Launch Control, T-minus 1 hour, 58 minutes, 15 seconds, and counting. We're into preparations now for fueling of the Atlas V. And joining us here now in our broadcast booth in the Atlas Spaceflight Operations Center is Diana Calero, and she is the mission manager for TDRS-L for the Launch Services Program here at KSC. Diana, first of all, welcome. It seems like that we were just here, but yet it's been a year. Just under a year. So Diana is going to show us some of what's been going on, both with the TDRS-L spacecraft once it arrived, and also with the Atlas V rocket. So if we could go ahead and roll the tape, and Diana, tell us what we're seeing.
Sure. So here you see the TDRS-L spacecraft being offloaded from the C-17 cargo plane. It arrived on the morning of December 6th and from El Segundo, California. The TDRS-L spacecraft was built by the Boeing satellite systems there. And here you see it being transported to the Astrotech, which is the payload processing facility in Titusville. You see it now being taken out of its container and unpacked, and that's a good shot there of their SA antennas on the top, which are in a furled configuration, kind of like a little taco shell. That's how it was sent to us from Boeing, and that's how it was actually fits inside the payload fairing and launches in that configuration. So once it's painstakingly taken out of its container, it takes quite a while to make sure it's hoisted safely. It will be placed in a vertical configuration and onto its test stand. And here you see it being a nice picture of it being hoisted. There's a solar array panel in its stowed configuration, and there it is on its test stand. And while it's at the processing facility, it undergoes a series of tests to make sure that everything it still works and functions properly from its voyage from El Segundo, from the factory. Here you see it being encapsulated into the Atlas V payload fairing. This payload fairing is the extended payload fairing, which is about 42 feet long, and it's 4 meters in diameter. And there you see the nice TDRS-L logo that's actually hand painted onto the fairing. So once it is encapsulated, it gets hoisted and onto a transporter, and it'll sit there a night or two before it gets transported over to the vertical integration facility at the launch complex. And there you see it being transported, and it's about a 25-mile journey from Astrotech to the VIF. It's done in the middle of the night, probably about 1 or 2 a.m. It takes about 3.5 or 4 hours to complete its journey. Here you see the Delta Mariner, which is the ship that brings the Atlas booster and Centaur from the Decatur factory. And you can see that's quite a big ship there. You see the booster and the Centaur in there. The booster, just to let you know, is 106 feet long and 12.5 feet in diameter. And right next to that is the Centaur, which is about 42 feet long and 10 feet in diameter. Now you see it being the 2 stages being transported to the Atlas V Space Flight Operations Center, which is about 7 miles up the road on the on Cape Canaveral Air Force Station. Once it gets to the ASOC, it'll go through a series of tests in the horizontal position to make sure a lot of the all the different systems are functioning properly. And once it finishes their horizontal processing, they're ready to be transported to the VIF. And here you see the booster on its way to the VIF. And once it arrives, it'll be hoisted and placed in the vertical position and mounted inside the VIF. And you'll see here a shot of it being hoisted, and then you'll see the 2 engines. Is a good shot of the 2 engines, the RD Amros RD-180 engines. Those engines produce about 160,000 pounds of thrust, and it burns RP1 and LOX. So once the booster is placed there, in a day or so, the second stage, the Centaur, will be transported to the VIF and get hoisted on top of the booster. The VIF is about 280 feet tall, so and this is a 401 vehicle, so this one isn't the biggest Atlas V. And here you see a good picture of the Centaur coming out of the ASOC and being transported to the VIF. The Centaur has the Aerojet Rocketdyne RL-10A engine, and with the Centaur uses a cryogenic fuel, so it burns liquid hydrogen and liquid oxygen. And so here you see it being hoisted, and it will actually be mated on top of the booster. And once the 2 segments are completed together, they'll run some tests and a combined systems test to test the 2 systems working together. So you have now the complete rocket. Now it's just waiting for the spacecraft to come. And here you see the encapsulated teacher cell spacecraft in the payload fairing. It arrived about 6 a.m. on January 13th. And here is the payload fairing with the spacecraft being hoisted up to the VIF. And you'll see it being mated now to the top of the Centaur. And now it's just waiting there to be rolled out to the pad. It was rolled out yesterday, and it sat there overnight. They loaded the RP1 fuel yesterday, and now we just went into the cryo tanking, and so it's sitting there, and all systems are go so far.
So having worked two flows together, was each one distinct in character or pretty much the same?
Well, they were pretty much the same insofar as most of the testing and everything was done at the factory. So it was really sent over here and just ran a few tests to make sure everything was functional. Although the Teacher's K, we didn't, obviously once you run one mission, you do some lessons learned, and we were able to apply some of these lessons learned for the teacher cell flow, which obviously helped a lot.
Well, Dinah, thank you very much, and best of luck. And we still have a good bit of the countdown to go, but everything seems to be going well. Thank you very much.
Thank you.
At T-minus 1 hour, 50 minutes, 19 seconds and counting, this is Atlas Launch Control.
I have one range safety closure for tonight of 02:13:00 Zulu.
Roger. T-minus 1 hour, 50 minutes. CLC performing comm checks on countdown net 1. NSC.
Loud and clear.
NLM.
NLM channel 1.
NLM.
This is NLM.
And have you loud and clear?
I read you loud and clear as well.
SMD.
It's SMD. I have you loud and clear.
LDD.
LDD reads you loud and clear.
TD.
TD, read you loud and clear.
NCE.
NASA CE, loud and clear.
Completes comm checks.
LC step 220, CFA purge in displacement mode.
Roger.
LC step 320. The FTS cycle test is complete. The FTS receivers are secured.
Roger.
LC step 270, Centaur LO2 transfer line shutdown is complete.
Roger.
LC, ECS on 1.
Go ahead.
Operation 50, step 270, and step 360. ECS has been on GN2 a minimum of 30 minutes.
Roger.
LC, step 270. CEC safing purge is active.
Roger.
CEP on high flow.
Roger. Start Centaur LO2 tanking.
Roger.
Centaur Max LC.
Go ahead.
Perform Centaur LH2 SVV cycle test.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 44 minutes, 25 seconds and counting. We have an update on our collision avoidance quotient for tonight. There is just one during our 40-minute launch window. That's a 1-minute cutout in the window that will occur at 9:13. Otherwise, the entire duration of the 40-minute window is open. So that will not pose any significant problem for us, especially if we launch right on time. And as we've heard, our tanking operations are now getting underway.
Is complete.
Roger.
At T-minus 1 hour, 43 minutes, 45 seconds and counting, this is Atlas Launch Control.
T-minus 1 hour, 43 minutes.
Secretary Load 2 at 10%.
Roger.
LC, ECS.
Go ahead.
Yeah, Port Operation 50, Step 370. Payload and CEM ECS has been on GN2 for 40 minutes minimum.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 39 minutes, 56 seconds, and counting. And joining us now here at our console in the Mission Director Center is Vern Thorpe, who is the Program Manager for NASA missions from United Launch Alliance. And Vern, welcome once again. I know you've been monitoring the tanking operations. Can you tell us real briefly where we are in tanking and what's going on?
Yeah, thanks, George. About 10 minutes ago, we came out of a planned hold. It's the hold that we have to make sure that we're ready to begin cryogenic tanking. It's our last opportunity to assess the state of the vehicle, the spacecraft, the range, the weather, and things look good. We've got one, what we hope is a minor radar issue on the range that we're working with. The spacecraft and launch vehicle are healthy, and we have begun our cryogenic tanking operations.
Vern, this is really a very busy year coming up for United Launch Alliance, and besides just our tracking data relay satellite mission coming up, what else is on your calendar?
Well, ULA's been pretty busy for the last 7 years. That's how old we are, and we've been launching almost once a month ever since we formed. This will be, I believe, our 78th launch just over 7 years. So that's almost one launch a month. This year we're actually going to ramp that rate up a little bit more. Right now we've got 15 missions on our manifest. We've got 10 launches planned from the Cape here in Florida, 5 launches planned from Vandenberg Air Force Base, and including tonight's launch, 5 of those, a third of our manifest, will actually be launches for NASA. We've got TDRS tonight. We've got a couple of science missions on Delta II later this year. We've got one more Atlas later this year, and then we've got a big launch in support of NASA's exploration program. It's actually a test flight of the Orion capsule on a Delta IV Heavy. That's scheduled for this coming September.
Well, Vern, let's talk a little bit now. After the Atlas V lifts off, it's got a fairly busy flight profile with one fairly significant coast period, but walk us through now. We'll look at the video and you can tell us what we're seeing.
Sure. Okay, that is what the vehicle looks like right now on the pad. This is actually a video from a previous launch, but we're going to use the Atlas V 401 configuration for this mission. That's the smallest of our Atlas Vs. And we do not require any solid rocket boosters on this mission. So the first major event that you'll see after liftoff will occur 4 minutes into flight. And at that point, we will have used up the propellants in the first stage, that booster stage that you see burning right now. And 4 minutes into flight, when the propellants are used up, you'll see here in just a moment, we'll shut down those engines. And then we fire some retro rockets to back that first stage away from the Centaur upper stage. A few seconds later, we begin flowing propellants through the engine on the Centaur to thermally condition it, and a few seconds after that, we'll actually light that engine for the first of 2 burns for this mission. That first engine burn will last not quite 14 minutes, and it will put the vehicle in a slightly elliptical orbit. You saw the payload fairing come off there. That'll happen 8 seconds after the engine burn starts. After that 14-minute engine burn, we'll coast for, it's about an hour and 20 minutes, about an hour and 22 minutes. That will get us into position for the second burn that you see here. That second burn will last about 1 minute, and that will put the satellite into a geosynchronous transfer orbit. That means that it'll coast up to geosynchronous altitude. It'll take us about 5 minutes to reorient to the proper separation attitude. At that point, we'll separate the spacecraft, as you see right here, and then we'll do the usual series of maneuvers with the upper stage to make sure that we don't contaminate or come into contact with the spacecraft, what we call our collision and contamination avoidance maneuver. Basically, we'll put the upper stage into a safe orbit, and that will all happen about 2 hours into flight. We'll separate the spacecraft about 1 hour and 45 minutes after liftoff.
And what's the reason we have such a long coast tonight?
It's because of the type of orbit that the spacecraft needs. One of the reasons is because we want to raise the perigee. We want to raise the closest approach to Earth on the final orbit that we put the spacecraft into. So during that long coast, not only will we get into the right position around the Earth to do the second burn, we'll also gain a couple thousand miles in altitude as well. And by doing that, that's a couple thousand miles less that the energy or less energy that the spacecraft has to expend with its own propellants to raise that orbit. So it's to maximize the amount of performance we give the spacecraft, so that in turn the spacecraft can maximize the amount of propellants that they have on board for station keeping once they get into their final orbit.
Well, Vern, thank you very much, and we'll be looking forward to launch tonight and all the upcoming other additional launches this year. So thank you very much.
Okay, thanks, George.
And we're now at T-minus 1 hour, 34 minutes, 28 seconds and counting. This is Atlas Launch Control.
Payload 2 at 40%.
Roger.
T-minus 1 hour, 32.
Pressurized Centaur LH2 storage tank to chill down level.
Roger.
LC, step 360. RP1 pressure decay test is complete, and RP1 tank is stable at step 2 pressure.
Roger.
ECB stable at prefill.
Roger.
RD-180 has been on heated GN2 for 20 minutes minimum.
Roger.
Atlas LO2 ground chill down is complete.
Roger. Start Atlas LO2 tanking operations.
Roger.
Payload 2 at 50%.
Roger.
LC, CFA purge has been in displacement mode for over 25 minutes.
Roger.
T-minus 1 hour, 30 minutes.
Kilo 2 at 60%.
Roger.
LC CLH.
Go ahead.
Op 50, step 370. Centaur LH2 storage tank at chill down pressure.
Roger.
Kilo 2 at 70%.
Roger.
LC step 370, Centaur LO2 at 75%.
Roger. Start Centaur LH2 transfer line chill down. Roger.
This is Atlas Launch Control, T-minus 1 hour, 25 minutes, 26 seconds, and counting. Joining us now is Jeff Gramling, who is the TDRS-L project manager from NASA's Goddard Space Flight Center, and has been with us for most of the flow of TDRS-L. And Jeff, having done a couple of these, how would you compare the two in terms of the way we've prepared them for flight? Has it been pretty much the same, or have there been some distinctions?
No, so far, TDRS-L has actually had a very clean flow, and this evening we've been fortunate. We've had a very clean count this evening, so we're looking forward to a beautiful launch in about an hour and a half.
Well, we'd like to, we talked some about the flight. Vern Thorpe told us what's going to be happening on the Atlas V, and taking us up through spacecraft separation. So if you could tell us some about the what's going to happen to the spacecraft as soon as it comes off the rocket in the first few minutes, in the first few hours, and then a little bit more about how it fits into the Constellation. So let's go ahead and roll the video.
All right, what you see here is the spacecraft is just been released from the Centaur upper stage, and soon after, an hour or so maybe after we separate, then we would send the commands to unfurl our single access reflectors. We're trying to get them unfurled as soon as we can so that the composite materials don't take a set. Then it actually is about 10 days to get to geosynchronous orbit and 5 burns. And once we're at, and that is performed out of Boeing's control center in El Segundo, California. Once we get to geosynchronous orbit after the 10 days, then we would start doing spacecraft deployments. Everything else besides the unfurling of the reflectors happens when we get to geo, and what you've just seen is one by one the single axis reflector booms are deployed, the solar arrays are deployed, and then our forward Omni and space ground link antenna, which points at our ground station at White Sands, New Mexico. Once the everything's been deployed and we've done the checkout, then we would hand over from the Boeing Control Center to our ground station for the TDRS system, which is in White Sands, New Mexico. And once there, we would complete the payload on-orbit test program. What you're seeing now is just kind of a day in the life of the TDRS system. You know, we've got 6 operational spacecraft in the geosynchronous belt, and that was a nice animation our folks have put together just to give you an idea of how busy the Constellation is on a day in and day out basis. And so I think it's a nice animation that helps people appreciate just how busy the system is and how important it is to lots of NASA user missions.
And do you stay in touch with how the spacecraft is doing back at Goddard, or do you go out to White Sands, or how does that work?
So we have during the 10-day transfer orbit, we have a team that's out located in the Boeing facility with the Boeing folks who we've been working with for many years to get where we are, which, as you know, George, we had a very successful launch of TDRS-K last year. Same thing. Once we launch and we complete the transfer orbit, we get everything deployed. Then we've got about 3 months of testing that we do from White Sands, and that's our staff again with the Boeing folks, but operating out of White Sands. Once the on-orbit test program is completed, then we would turn it over to another organization at Goddard that operates White Sands and the operational fleet, and they would look at the health of the Constellation and determine where they're going to drift this spacecraft. In other words, which part of the Constellation they would move it into.
Well, Jeff, thank you very much, and best of luck tonight. And we'll be looking forward to those first signals coming back from TDRS once it's up there later on tonight.
Great. Thank you, George.
Thank you. And we're at T-minus 1 hour, 21 minutes and counting. This is Atlas Launch Control.
LC, step 430, Centaur LO2 at 96.4%. Popping started.
Roger.
Atlas LO2 at 10%.
2 minutes, 1 hour, 20 minutes.
Roger.
AHB is at flight pressure.
Roger. Centaur bottles at flight mass. Roger.
This is Atlas Launch Control, T-minus 1 hour, 17 minutes, 8 seconds, and counting. Once the Atlas V lifts off, it will move downrange on a launch azimuth of 101.4 degrees, slightly south of east. It will go through the sound barrier almost exactly 1 minute into the flight, and then the maximum dynamic pressure on the vehicle occurs at launch plus 91 seconds. When the spacecraft separates from the Atlas V, it will be in an elliptical orbit of 19,324 miles by 2,613 miles. That would be the nominal orbital parameters at separation. And we have just passed the 20% mark on filling liquid oxygen onto the stage, and All our tech activities are on schedule, and we're not working any issues, so at this time we continue to target a 9:05 p.m. liftoff. At T-minus 1 hour, 16 minutes, and counting, this is Atlas Launch Control.
T-minus 1 hour, 15 minutes.
LC step 460, Centaur LO2 at flight level.
Roger.
Atlas LO2 at 30%.
Roger.
LC, CFA purge has been in displacement mode for 45 minutes.
Roger. Start CFA purge to control mode.
Roger.
T-minus 1 hour, 10 minutes.
LC, CISA ECS set point has been reset for 15 minutes minimum.
Roger. Initiate Centaur engine chill down.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 9 minutes, 15 seconds, and counting. Since the launch of NASA's first payload into space, there's been a need to communicate with the spacecraft. The video that we're going to look at now explains this need and the vital role of the TDRS system to communicate this critical data between spacecraft and ground controllers.
NASA's constellation of tracking and data relay satellites, TDRS, are the critical link for continuous space communications. But it wasn't always this way. Before TDRS, NASA relied on a web of ground-based tracking and communication stations located around the globe. These ground stations use large antennas to receive early transmissions from space. The different orbits of these spacecraft determine the locations of ground stations, with the majority being centered around the equator. Sometimes even ships and planes that house antennas were used to fill in holes of coverage between spacecraft and user control centers. During this period, these early spacecraft only had a few moments to transmit their data to each station as it traveled on its orbit, passing from horizon to horizon. In an attempt to increase visibility with the ground, the number of these ground stations around the world multiplied. As time passed, these networks evolved and merged, but they often suffered from a variety of challenges such as regional weather and political instability. With the advent of the shuttle program, NASA began to see the need for an improved solution. The TDRS project was established to develop a constellation of satellites that would be designed to route data between the user spacecraft and the ground for critical NASA missions in low Earth orbit. The 10 TDRS spacecraft that have been deployed since 1983 have transformed the way NASA communicates. Each TDRS spacecraft is placed in a geosynchronous orbit, giving them a fixed line of sight with one of the TDRS ground stations. Today, TDRS spacecraft relay data between Earth-orbiting satellites and the dedicated TDRS ground terminals 24 hours a day, 7 days a week. 3 TDRS ground terminals provide a constant connection between the TDRS constellation and the user spacecraft's data processing facilities. 2 of these stations are located at the White Sands Complex in New Mexico, and the third is located in Guam. Together, the ground stations in the fleet of TDRS spacecraft provide 100% global communication coverage, ensuring that data from dozens of Earth-orbiting missions is delivered on time, every time. TDRS provides a vital service to Earth science missions studying the evolution of Earth's climate and researchers postulating about the future of the Earth system. These missions are delivering data in real time about Earth events and processes vital to human civilization. TDRS communicates with launch vehicles as they send missions on their journeys of discovery. TDRS tracks their locations as they leave the launch pad, ensuring that engineers on the ground know that the vehicle is on the right course and is functioning properly. TDRS provides critical voice and video support to NASA's human spaceflight endeavors, including ongoing support of the International Space Station and its critical resupply vehicles. TDRS supports space science missions that investigate the farthest reaches of space, cataloging gamma-ray bursts, the birth of galaxies, and the early history of our universe. Through them, we can learn new information about the scope and scale of the cosmos. NASA is adding a new spacecraft to the TDRS constellation, ensuring the critical lifeline of space-to-ground communication support will be available for many years to come.
T-minus 1 hour, 5 minutes. Atlas LO2 at 50%.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 1 minute, 30 seconds, and counting. Right now we're chilling down the Centaur engines in preparation for loading liquid hydrogen onto the vehicle, which will begin in about another 45 minutes or so Right ahead of that, we'll have a launch weather briefing from our launch weather officer, Clay Flynn. The RP-1 liquid fuel was loaded aboard yesterday afternoon after the rollout to the pad. We just had confirmation that the liquid hydrogen chill down is complete and tanking will begin shortly. At T-minus 1 hour, 43 minutes, 42 seconds, and counting, this is Atlas Launch Control.
Adjust CEM ECS temperature per TRD.
Roger.
Atlas LO2 at 60%.
Roger. Initiate BRC ECS.
Roger.
AHBs at flight mass.
Roger.
Atlas LO2 at 70%.
Roger.
T-minus 55 minutes.
Start flight control final preps.
Roger.
This is Atlas Launch Control, T-minus 54 minutes, 40 seconds, and counting. Joining us now in the broadcast booth here in the Atlas Spaceflight Operations Center is Jim Norman, who is the Director of Launch Services Human Exploration and Operations Mission Directorate at NASA headquarters. And Jim, tell us, first of all, a little bit about what that is and what your office does.
Thank you, George. You bet. I'm pleased to work in the Human Exploration and Operations Mission Directorate as the Director of Launch Services. That means that I get to provide myself and a small staff, about 4 folks, provide oversight and strategic guidance to the Launch Services program. What that means is that we tend to be the Washington interface, dealing on policy issues, budgetary guidance, and providing strategic guidance with acquisition issues.
Now, how would you perhaps be working with the folks at SCAN?
So my colleague, Roger Eunice, is the director for SCAN there at headquarters, and so he and I work together when it's time for us to launch one of his satellites, and then his directorate also supports many of our launches with the constellations that he has on orbit.
And about how far out might he be talking with you about something?
Well, it depends, obviously, on the mission. We're talking, frankly, constantly on various issues there at headquarters. But a mission flow begins typically 3 years out.
So as we go down the chain a little bit, what is Launch Services Program, and how do they work with you?
They're a great bunch. Launch Services Program, as most people know, is based here at Kennedy. The program manager, Amanda Miskevich, reports to me. She has a great team. Her and her deputy, Chuck Duval, have put together a terrific group here to do the Launch Services program. They're responsible for doing the acquisitions and providing the launch management for the commercial launch services that we procure. They do a great job working with the various customers, both within NASA and, frankly, across the civil sector, to make sure that we're able to procure launch services when our customers need it. And they have a great teaming relationship, I believe, with industry in order to provide very successful rides to the missions that need to get to orbit for NASA and the other civil missions.
So how often are you in communication with the Kennedy Group?
Quite often. We're speaking pretty much daily on various issues, and us letting them know about different things in terms of the environment. In DC, communicating, make sure we're coordinated there. One of the main features that my office does is work the interface with the Science Mission Directorate. And so my staff of 4 is communicating with them. And I'm communicating with, again, Amanda and Chuck quite often on various issues.
Well, Jim, thank you very much, and gives us some understanding about how that all fits together into an entity that ultimately leads to like a launch that we're having tonight.
And we're all looking forward to a good ride here for the satellite tonight as well.
And we're now at T-minus 51 minutes, 8 seconds and counting. This is Atlas Launch Control.
Atlas LO2 at 80%.
Roger. Pressurize ECB to flight pressure.
Roger.
CLH2 at 40%.
Roger.
T-minus 50 minutes.
CLH2 50%.
Roger.
CLH2 60%.
Roger.
This is Atlas Launch Control, T-minus 46 minutes, 45 seconds, and counting. Loading hydrogen onto the Centaur is already underway, and our countdown continues to go well. We're not working any issues, and weather continues to be green. So we're go for a 9:05 p.m. launch tonight. Upon liftoff, tracking of the Atlas V rocket will be done by the Eastern Range, beginning with the antennas at Cape Canaveral Air Force Station and Kennedy Space Center. At a minute 13 seconds after liftoff, the Air Force downrange station near Jupiter Inlet in South Florida will also acquire the rocket and begin providing data. Then the last Eastern Range ground station to acquire will be at the island of Antigua in the Caribbean, which will take over supplying data immediately prior to loss of signal from Florida. Antigua will be supplying data until approximately 14 minutes into the flight, at which time data will be coming from the TDRS East tracking and data relay satellite. As the rocket approaches the far side of the Earth, the Indian Ocean TDRS will begin furnishing data, as well as the Air Force tracking stations at Diego Garcia and Guam, which will be also covering that spacecraft separation, which occurs 1 hour 46 minutes after launch. Once TDRS-L is on its own, the initial contact will then be made through the Dungara tracking station on the west coast of Australia. At T-minus 45 minutes, 18 seconds and counting, this is Atlas Launch Control.
CLH2, 80%.
Roger. T-minus 43 minutes.
CLH2, 90%.
Roger. T-minus 42 minutes.
ECB at flight pressure.
Roger.
Atlas LO2 at 97.5%, topping started.
Roger.
T-minus 40 minutes.
Start final open loop FTS test.
Roger.
LCCLH.
Go ahead.
Op 50, step 620, Centaur LH2 at 96.2%, topping started.
Roger. Perform Centaur LH2 fill and drain valve cycle test.
Roger.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
Atlas LO2 at 99.6%.
Roger. Cycle Atlas LO2 fill and drain valve.
Roger.
Perform Atlas Airborne LO2 vent valve functional test.
Roger.
For the team on net 1, this is the LC, showing complete through step 620.
CLHLC.
Go ahead.
Centaur LH2 fill and drain cycle test complete.
Roger.
I'll see the CLO Centaur LO2 fill and drain valve cycle test is complete.
Roger. Perform Centaur SRV and LH2 SVV cycling tests. Roger.
This is Atlas Launch Control, T-minus 35 minutes and counting. NASA's tracking data relay satellite Constellation has evolved over the years. The following video that we're going to see tells the story of TDRS, the network that enables exploration.
In the late 1970s, satellites such as the Nimbus 7 satellite relied on NASA's ground stations located around the world to provide a communication network. This ground-based network could only provide communication over 15% of the satellite's orbit. With its ever-expanding orbiting fleet of satellites and manned spaceflights, NASA had to increase the coverage and develop an improved way to track and communicate. In 1983, NASA launched the first of a series of new communication and navigation satellites that would rely less on international ground stations and provide continuous coverage. Tracking and Data Relay Satellites, TDRS, are a network of geosynchronous communication satellites that work in conjunction with two ground stations. Today, NASA's fleet of spacecraft and launch vehicles, like the Tropical Rainfall Measuring Mission, TRMM, can communicate and navigate with the help of TDRS. This interaction between TDRS and the spacecraft is a series of complicated signals that guarantees that every Earth-orbiting spacecraft will have nearly non-stop coverage. The International Space Station, ISS, routes voice and video communications along with data through the TDRS fleet. The Hubble Space Telescope also utilizes the full capabilities of TDRS. TDRS supports the Hubble's real-time interactions with the ground systems, allowing observers to make small adjustments to its observatory system. TDRS provides the Earth observing system of satellites, such as the Aura spacecraft, with low-latency data relay and navigation data. The TDRS network sends all of these data streams and voice communications to either the White Sands complex in New Mexico or the Guam Remote Ground Terminal. Guam then transmits the data it receives to White Sands. The White Sands complex then relays it to the end user at their mission's operations centers. As long as there's space exploration, TDRS will be working side by side with spacecraft and end user, providing continuous connectivity for navigation, data, and voice communications.
T-minus 32 minutes. T-minus 31 minutes.
This is Atlas Launch Control, T-minus 29 minutes, 35 seconds and counting. We have one remaining hold coming up. That's a 10-minute planned built-in hold that will be coming up in about 25 minutes or so at 8:51. We're going to look now at some time-lapse of the rollout of the Atlas V to the launch pad yesterday, which occurred at about 10:22 in the morning.
LC ALO.
Go ahead.
Step 640, Atlas LO2 fill and drain valve cycle test is complete.
Roger.
Atlas airborne vent valve functional test is complete.
Roger. Perform pogo suppressor charge.
Roger.
LCRF.
Go ahead.
LC step 820. The FTS open test is complete.
Roger. T-minus 25 minutes.
This is Atlas Launch Control at T-minus 24 minutes, 38 seconds and counting. Our launch tonight is dedicated to Skip Mackey, NASA's flight commentator after liftoff in the Hangar AE telemetry facility, who passed away on November 19, 2013. For most of 40 years, Skip called all the flight events of the rocket as they occurred, watching and calling out the data as it came back from all the downrange tracking stations. As far back as the 1960s, following every unmanned launch, the only voice you would hear over the communications channels after liftoff was the voice of Skip Mackey. Skip was the flight commentator for all of NASA's science, planetary, and communications launches. There were many launches back then. Most went well, some went badly, but you could always count on Skip to remain constant, letting you know how the flight was progressing. In more recent years, the video camera set up in Hangar AE would catch the image of a frantic Skip running from archaic strip chart to strip chart, enthusiastically calling out critical rocket milestones for all to hear. Whether you were a cape worker on console for launch or a launch guest at a viewing site, you relied on Skip to tell you how the rocket was performing on its mission and flight into space. Skip had a knack for quickly and accurately translating all of the telemetry data he was seeing into a clear and concise message for everyone to understand. He was particularly effective in describing events that the everyday person could clearly understand what was happening. In other words, he boiled down the jargon, so you didn't have to be an engineer to get it. Yet it was done with an enthusiasm in his voice as he watched the data of critical milestones coming in which kept everyone listening for the excitement that he generated in every word. When not working a launch, Skip was always willing to teach new engineers what he knew. He was aware that not everything was written down, so he took it upon himself to teach others. Skip was a boss to some, and co-worker and mentor to many others. He left his legacy with engineers and launch personnel throughout the space industry at Cape Canaveral. A legacy that hard work, intelligence, commitment, enthusiasm, friendship, and love can all coexist and flourish. He'll be missed dearly by his NASA and his United Launch Alliance family. At T-minus 22 minutes, 12 seconds and counting, this is Atlas Launch Control. This is Atlas Launch Control, T-minus 20 minutes, 27 seconds, and counting. In just a moment, we'll hear from our Launch Weather Officer, Clay Flynn, in the 45th Weather Squadron, updating us on the weather for the upcoming launch tonight.
T-minus 20.
Conduct weather briefing on Channel 8 Weather Conference Net.
Roger that. LWO, range coordinator, Channel 8.
LWO.
LWO, please stand by for weather brief.
Standing by.
Following personnel acknowledge standing by on Channel A for weather brief. NLM.
NLM.
LD.
LD.
AFLD.
AFLD.
LWO, please proceed with your weather brief.
Yes, sir. This is LWO on Channel 8 Weather Brief and CC Local. You should have a satellite picture of the peninsula of Florida on your CCTV monitor at this time. And you look to the north, you see those clouds streaming from west to east. They should remain to the north through the balance of the window. Likewise, the clouds to the west should remain to the west through the end of the window. Taking a look at the radar, no echoes on the radar. Not expecting any precip. We'll monitor for a very low threat of any type of thick cloud on the radar, but otherwise conditions are very favorable. In terms of the winds out at Complex 41, have trended up just slightly, gusts in the mid-teens, and we should stay in the mid-teens. Actually, you got a gust to 17 knots on the northwest tower, I noticed. So mid-teens through the balance of the window, perhaps upper teens, but that should be about the peak of it. We'll gradually trend up late this evening with the frontal boundary trying to increase the pressure gradient. In terms of the wind direction, wind should stay out of the north for the balance of the count and the window. In terms of our temperature, presently we're at 55 and should lose just a degree or two with the winds coming off the water during the balance of the count and the window. This is multiple balloons, a pretty good agreement between the balloons, and not expecting significant change to the balance of the count and the window. In terms of the forecast, looking at scattered at 20,000 feet, 7 miles visibly, no significant weather. Winds from the north at 10, gusting to 15, really should probably bump that up just a couple of knots for the balance of the window or the latter part of the window. Temperature 54 to 53, and just a 10% chance of violation that's associated with thick clouds, but it's a very low threat. All LCCs are go and expected to remain go through the count. No change in the 24-hour delay, and no lightning threat and no wind threat through the balance of the count in the window. This concludes the weather brief. Pending your questions, sir.
Range coordinator has no questions.
NLM has no questions.
LD, no questions.
AFLD, no questions.
T-minus 17 minutes.
Engine FIV is closed.
Roger. T-minus 16 minutes.
Initiate fuel fill sequence.
Roger.
T-minus 15 minutes.
Flight control final preps are complete.
Roger.
Primary adjust, TechX file, adjust, _ alpha, Victor, 043, _05 with SDL CRC Echo 42 Echo has been received, verified, and is ready to load into the FTANU.
Proceed with load.
Roger.
This is Atlas Launch Control, T-minus 14 minutes and counting. The final parameters being loaded on board the guidance computer, consisting of upper-level winds and other flight data that the flight computer needs to help steer it through the upper atmosphere as it heads towards space. At this time, we're not working any issues. We're on schedule for a 9:05 liftoff. At T-minus 13 minutes, 36 seconds and counting, this is Atlas Launch Control.
T-minus 12 minutes.
And now coming to us through a downlink from a TDRS satellite is the crew of the International Space Station.
Hi, I'm Expedition 38 Flight Engineer Mike Hopkins of NASA, aboard the International Space Station with my crewmate Rick Mastracchio. NASA and its industry partners are set to launch an Atlas V rocket from the Cape to place the newest tracking and data relay satellite into orbit. As you know, the ISS depends on the TDRS constellation to provide data and video to the world's flight control centers and to allow us to communicate with mission control in Houston, with the public, and with our friends and families.
On behalf of NASA and the international partners who rely on the amazing capability of the tracking and data relay satellites, best of luck with the launch. We'll be watching.
And we're standing by in less than 30 seconds to go into our planned built-in hold, or rather the 10-minute hold that occurs at T-minus 4 minutes. And we're now at T-minus 10 minutes, 13 seconds, and counting. This is Atlas Launch Control.
T-minus 8 minutes.
Switch all secondary decoms to RF link.
Roger.
T-minus 6 minutes.
Fuel fill sequence is complete.
Roger.
This is Atlas Launch Control at T-minus 5 minutes and counting. We're 1 minute away from going into our planned built-in hold. Our spacecraft has just gone into launch configuration for flight.
All steps are prior to entering the hold.
Com check.
Loud and clear.
Going into the hold in 5, 4, 3, 2, 1. T-minus 4 minutes and holding for 10 minutes.
Program 10-minute hold.
Com check, channel 1.
Loud and clear. OSM
And
LZ.
attention all stations on NLM net. This is NLM at L-13. We'll be performing the final launch poll. We've had a smooth countdown. We've got a great range. We've got a great rocket, and we've got a healthy spacecraft. So with that, I'd like to conduct the final launch poll and spacecraft configured for launch. Beginning with NASA CE.
NASA CE, go.
SMA.
SMAs, go.
SMD.
SMD, go.
NASA MEM.
NASA MEM is go.
NAM.
NAM's ready.
NLM copies. The NASA team is ready for TDRS-L launch.
CTP status verified.
Roger.
Red line monitor and event table are in the correct configuration for terminal count.
Roger.
Launch on time verified.
Roger.
This is Atlas Launch Control, T-minus 4 minutes and holding. We have approximately 6 minutes, 35 seconds until we pick up the countdown. We have confirmation that the TDRS-L spacecraft is on internal power. The vehicle that as we see it there, weighs 746,061 pounds, standing 192 feet tall. And weather is go, range is green. We're headed for an on-time launch at 9:05. T-minus 4 minutes and holding. This is Atlas Launch Control.
Verify solar radiation acceptable for launch.
Verified.
LC switch ready. Position. All steps are complete prior to the status check.
LCRC1.
Go ahead.
I have a launch window management plan good through 0245 end of window.
Roger. Status check to proceed with terminal count. Atlas Systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur Systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical Systems, airborne.
Go.
Ground.
Go.
Facility. Facility, net 1.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
Com.
Go.
Timer.
Go.
GC cube.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Range coordinator.
Clear to proceed.
Launch director. LD net 1. LD. Status check to proceed with terminal count.
Permission to launch.
Proceeding with the count. T0 is planned for 0205Z. Set count to start at 0201Z.
Roger. T0 is set for 0205 Zulu. Count will start 0201 Zulu.
This is Atlas Launch Control. We're now 1 minute away from picking up our count.
On internal power.
Spacecraft is confirmed to be on internal power. "30 seconds away from picking up our countdown at T-minus 4 minutes.
On my mark, time will be T-minus 4 minutes and counting.
LC, LD, do not pick up the count.
LC switch.
LC, this is LD on channel 1. Do not pick up the count.
Roger. Timer, do not release the hold.
Atlas Launch Control standing by to see why the count has not picked up.
LD, LC.
LD.
Clock was stopped.
I copy that. The SV was not go. Stand by for a ETRO.
Roger.
LC, comma 1.
Go.
Roger, sir. We're going to have to do a complete recycle of the clock. There was not enough time to extend the hold.
Roger. Timer, LC.
Go ahead.
Picking up at step 1260. Reset countdown clock to T-minus 4 minutes and holding. Set initial hold to 10 minutes.
Roger, and work.
LCLD channel 1.
Go ahead.
So the SV reports some dropouts in their telemetry data. Will you initiate a anomaly discussion?
Roger. AC, LC on 1.
AC on 1.
LD has reported the hold call was for data dropouts of the SV. Please take this over to the Anomaly net for discussion and provide recommendation.
Roger, going to 6.
This is Atlas Launch Control. The account did not pick up because of some data dropouts from the vehicle seen in the telemetry, and they're now discussing what was actually observed.
Go. Roger, sir. Clock is reset. T-minus 4, holding for 10 minutes.
Roger. Flight control LC.
Go ahead.
Clear option 910, wait.
Roger. Option 910, wait, cleared.
Roger. Redline monitor. Perform redline monitor recycle.
Roger.
This is Atlas Launch Control, T-minus 4 minutes and holding. There is a discussion underway about why the telemetry dropouts from the launch vehicle are being seen, and what the options are for this going forward. They're still trying to determine what it was that was happening and why it was happening. And this discussion is going to be going on for a few minutes, it appears, still. But this was called by a member of the launch team, and it is a required hold to hold the count. If they are seeing any data dropouts like this, a hold is mandatory. So what happened is exactly what the procedure dictates, and we did not pick up the count. That is in the countdown rules. So right now they're trying to figure out why these hits were occurring and what else, what would occur if we were to proceed. So it's still under discussion, and we'll keep you updated as we find out where and how these telemetry dropouts, these data hits as they're being called, are happening. T-minus 4 minutes and holding. This is Atlas Launch Control.
LD, LC, Net 1. This is LC on Net 1. Our recycle from attempting to pick up the clock is complete. All personnel maintain system readiness, and we will pick up with the pole at L7 once a new T0 is coordinated.
This is Atlas Launch Control, T-minus 4 minutes in holding. And we're here now with our assistant launch manager, NASA assistant launch manager for tonight's countdown, Omar Baez. And Omar is going to give us a discussion about what it is that's happened, why did we not pick up the count, and what's been going on to help try to get us back on track. Omar?
Sure. George, what we experience is the spacecraft has various forms of receiving data, health data from the spacecraft to see how it's doing. One of the forms is through radio frequency, or RF as we call it, or hardline, the wired connection through the launch vehicle up the umbilical tower and down to the ground. At about 18 minutes, we switched sources from the ground source to the RF, or the radio frequency source, which is what we'll use when the spacecraft is on ascent. And they started to see some frame dropouts of the data at about 5 minutes and 20 seconds. And so right before we picked up the count, we called the hold because it was would have been in violation of one of their several of their mandatory constraints, and so that's a call to hold the launch, and we did. So now what the resolution will be to continue monitoring that data through the hardline source, through the launch vehicle and the umbilical tower, and at T0 switch the source from the hardline over to the radio frequency source, and we'll not be violating any of our constraints going forward, and should be able to monitor the spacecraft on ascent.
So this is this correct to say this is a workaround to this issue?
There's several ways to work it, and this is one of the workarounds to be able to accomplish the launch.
All right, so at this point, I think we just await when they think our next T0 will be.
Right. They were, as I came down here, they were just closing out the Anomaly, and they are selecting a new T0 as we speak.
All right, well, thank you, Omar, and we'll stand by to see how we come out of this and what our new T0 will be, and if not, maybe we can call upon you again if we have to extend this a little bit further. So thank you very much, Omar. We're at T-minus 4 minutes and holding. This is Atlas Launch Control.
The situation, the cause of the interleave telemetry dropouts that the spacecraft was reporting is apparently due from multipathing from Tel4 RF source. The recommendation of the Anomaly team is to have Hangar AE switch their data source back to the hardline telemetry and maintain the hardline telemetry as their source until confirmation of liftoff. And at that point, they would then switch their source back to the RF link. And following those actions, the recommendation is to proceed through launch.
LC concurs. NLM?
NLM concurs.
LD?
LD concurs.
LC, AC on 1.
Go.
Roger, sir. I can confirm that the interleaf data source has been switched back to hardline at hangar AE.
Roger.
Right now we're standing by for confirmation of a new T0. The time under discussion is 9:33, and we're waiting for confirmation of that. So that would mean we would be picking up the count at 9:29.
LCLD, channel 3, or channel 1, excuse me. Go. Let's see, please coordinate a new T0 of 02:33:00 Zulu.
Roger. RCLC?
LCRC1, go.
Please coordinate a new T0 of 02:33:00.
02:33 Zulu in work.
Timer LC? Go. Please set the clock for a new T0 of 02:33:00. Roger.
LCRC1,
go.
New T0 of 02:33 Zulu has been approved.
Roger. Of the NASA team on NLM Net, beginning with NASA CE. NASA CE, go. SMA.
SMAs, go.
SMD.
NLM, 1 sec. NLM, this is SMD.
LC column 1,
go.
NLM copy.
New T0
SMD,
0233.
NASA MEM.
NASA MEM is go.
NAM.
NAM is ready.
NLM copies. The NASA team is ready for TDRS-L launch with a T0 of 0233 Zulu.
LC switch to the ready position.
This is Atlas Launch Control. The launch conductor, Ed Kidda, will poll his entire team once again at about launch minus 7 minutes. We have a go from NASA Launch Manager Tim Dunn, who's polled the NASA team and the TDRS-L spacecraft team. And we are on hardline data now. Instead of RF. And they appear to have isolated this to some multipath in the RF signal. So they'll work around this using a hard line. Once again, our new launch time is 9:33. We'll pick up the count at 9:29. We're standing by for Ed Kidda, our United Launch Alliance launch conductor, to pull his team in the firing room. That'll be coming up in just a minute or so.
Status check to proceed with terminal count. Atlas Systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur Systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
HASGAS.
Go.
Electrical Systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
Timer.
Go.
GC Cube.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Ops safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Range coordinator.
Clear to proceed.
Launch director.
LD is go, and you have permission to launch.
Proceeding with the count. T0 is planned for 0233 Zulu. Set count to start at 0229 Zulu.
Roger. T0 is set for 0233 Zulu. Count will start at 0229 Zulu.
NSC, verify spacecraft is on internal power.
NSC can verify the spacecraft is on internal power.
All steps complete prior to terminal count.
Standing by now in about 15 seconds to pick up the count.
On my mark, time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting.
Minus 355.
Ground power enable.
Minus 340. Minus 330. Minus 315. T-minus 3 minutes.
Carrying LO2 topping.
Atlas tanks to flight pressure.
Minus 250.
FTS internal.
Minus 2 minutes.
Launch sequencer start.
Minus 150.
Securing Centaur LH2.
Securing Centaur LO2.
Minus 1.
FCS launch enable.
FTS armed.
Minus 130.
Countdown 9 being controlled by the launch computer.
20.
Clock is armed.
FCS count started.
Minus 110.
Vent valves locked.
Minus 1 minute.
Rock, report range status.
Range screens.
Minus 40.
Stable at step 3.
Minus 30.
Status check.
Go Atlas. Go Centaur.
Go Tetris.
Minus 20.
T-minus 15 seconds now, going into terminal count. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine ignition and liftoff of the Atlas V with TDRS-L, building our ability to meet the growing future of communications in space.
Booster view has gone to closed loop control. Picture roll program has begun. Vehicle body rates look good. Plus the battery voltages are stable. Tank pressures are as well. Booster engine continues to look very good. Pump speeds and injector pressures are within band. Roll program is complete. Vehicle body rates controlling right down the middle. Booster engine performance continues to look very good. Tank pressures are stable.
Vehicle going through the sound barrier at this time.
Mach 1. Max Q. Vehicle body rates continue to look very good, controlling right down the middle. Coming up on the booster throttle back, and we have throttle back right on schedule. Engine response looks good. Booster engine performance continues to look very good. And the booster has begun Q alpha limited steering as well as a small roll bias for telemetry. Body rates look good. And the liquid pyro valve for the RCS has fired, and now the pneumatic. That system is now pressurizing to flight levels. Signatures look good. Current altitude is 32
4.6 miles, downrange distance 57 miles, current velocity is 5,325 miles per hour. And the Q Alpha limited steering phase of flight has completed. Body rates continue to look very good. Tank pressures are stable. Booster engine continues to operate well for the set mixture ratio. Pump speeds and injector pressures within expected range. And the booster has begun to throttle to maintain 5 Gs in preparation for BECO. Boost phase cooldown is underway. Signatures look good. And we've begun to throttle back to 4.6 Gs for BECO. Boost phase cooldown is complete. And we have engine shutdown. BECO looks good, clean signature. We have retros and stage separation. Looks like a clean set. We have LOX and fuel pre-start. GN2 purge firing on the RCS is underway. We have ignition and full thrust on the RL-10. Looking for the payload fairing jettison momentarily, and we have indication of payload fairing jet. Looks like a good separation. And Centaur PU is being commanded to a LOX-rich mixture ratio for the early portion of this 834-second burn. Engine response looks good for the set mixture ratio. Closed loop steering has been enabled on Centaur. Vehicle is nulling out rates associated with the start transient. LO2 tank pressures have been ramped down and are stable. Current altitude is 113 miles. Downrange distance is 400 miles. Current velocity is 11,298 miles per hour. And we've begun seeing the thermal conditioning firings on the RCS. Signatures look good. Centaur body rates are now controlling right down the middle. The range track shows the vehicle making good progress right down the middle of the range. And Centaur PU is now in closed loop control. However, it continues to request an oxidizer-rich condition. This is expected for this point in the burn. RL-10 chamber pressures, LOX pump discharge, all look appropriate for the set MR.
Antigua has now acquired.
And we have had the format change, just a minor loss of data for the format change. Signatures all look good across the change. Quick review of the booster performance shows that the PE was plus 10 pounds, which is 0.1 sigma high. Centaur currently is at an altitude of 166 miles, downrange distance of 797 miles. Current velocity is 12,112 miles per hour.
We're hearing our telemetry engineer Marty Malinowski from United Launch Alliance.
RL-10 performance continues to look very good. Chamber pressures, LOX pump discharge, and fuel venturi inlets all within expected parameters. Centaur continues to request an oxidizer-rich condition as it works off the excess oxidizer. Continuing to see normal thermal conditioning firings on the RCS. Line temperatures are warming towards bottle temperatures. Centaur has now achieved the head-on gate. Range track continues to show good progress right down the middle. Current altitude is 182 miles, downrange distance 1,080 miles, current velocity 12,838 miles per hour.
Now losing data from the Cape, all data now coming through Antigua.
Centaur tank pressures are stable. Storage bottle pressures look good. Bus and battery voltages are within the expected range for this portion of the mission. Centaur PU has begun controlling off the oxidizer-rich mixture ratio at this point. Engine response looks good to the change in MR. RCS line temperatures have warmed to bottle temperatures. Current altitude is 184 miles. Downrange distance is 1,472 miles. Current velocity 14,039 miles per hour. At T plus 700 seconds, Centaur PU is now controlling near nominal MR. RL-10 engine performance looks very good. Chamber pressures, lax pump discharge, and venturi are appropriate for nominal MR. Hydrazine line temperatures have warmed to bottle temperatures. Tank pressures are stable. Storage bottle pressures look good. Bus and battery voltages are stable.
12 minutes, 10 seconds into the flight.
Range track continues to show good progress right down the middle of the corridor. Current altitude is 169 miles. Downrange distance 1,904 miles. Current velocity 15,509 miles per hour. There's approximately 5 minutes remaining in this first burn. All Centaur systems continue to perform well. Current altitude is 155 miles, downrange distance 2,185 miles. Current velocity is 16,501 miles per hour.
"14 minutes into the flight. Switching now from Antigua data to data through TDRS East.
And we have IIP vanish. Centaur is now orbital. All systems continue to look very good. RL-10 chamber pressures, pump, LOX pump discharge, and fuel venturis are appropriate for the near nominal MR. Tank pressures, storage bottle pressures are stable. Bus and battery voltages are stable as well. Current altitude is 132 miles. Downrange distance is 2648 miles. Current velocity is 18,267 miles per hour. A little under 3 minutes remain in this burn. All systems continue to look very good. A little under 2 minutes remain in this burn. Centaur PU is controlling near nominal MR. RL-10 performance is excellent. And we have 1 minute to MECO. Engine continues to perform well. RCS thermal conditions are excellent. Tank pressures are stable. Storage bottle pressures are as well. RL-10 engine performance continues to look good. Chamber pressure, LOX pump discharge, and venturi within expected range. Coming up on MECO momentarily. And we have MECO 1. Engine shutdown looks good. We have 4S settling motors on. Fuel tank pressures are being vented as expected. FTS has been secured. Centaur has begun its turn to the PTC attitude. It's also begun to spin up to the 1.8 degrees per second expected during the PTC. And Centaur has achieved 1.8 degrees per second in its roll as it continues to reorient to its PTC attitude. Tank pressures are stable. Storage bottle pressures are as well. Bus and battery voltages look good as we continue to settle with 4S settling motors. This coast is expected to last just over 82 minutes in duration. It'll be followed by a second burn of 1 minute and 1 second duration, followed by a short coast of 286 seconds till spacecraft set.
We're now 20 minutes 15 seconds into the flight of TDRS-L aboard the Atlas V. We're going to, now with the vehicle in a coast phase, we're going to take some time to look at some replays of the launch as it occurred just slightly more than 20 minutes ago. This is Atlas Launch Control, now 40 minutes into the flight of the Atlas V with TDRS-L, vehicle now in a stable coast phase. We're looking at a now empty launch pad at Complex 41. The securing teams have been cleared into the pad for securing, and all of the launch complex systems will now be safed, and the pad will be secured. We're going to look now at a short program about what TDRS-L, the launch and the mission, is all about. The next component in NASA's network of vital communication satellites will be placed into space this month to continue the task of relaying data and commands from Earth to the space agency's fleet of spacecraft. 30 years into its operations, the Tracking and Data Relay Satellite System has allowed NASA to expand its abilities to communicate directly with spacecraft like the International Space Station and observatories such as the Hubble Space Telescope, while being able to forego its network of ground-based communication stations around the world.
The TDRS Constellation brings back all of the data and video that we see every day from the International Space Station. In addition, TDRS supports all of the data from the Hubble Space Telescope and all of our low Earth orbit NASA science missions.
In other words, TDRS accomplished exactly what NASA designed it for. Its work is far from finished, however, and NASA's needs are not shrinking. That's why the agency is launching TDRS-L, the next member of the third generation of TDRS satellites.
TDRS-L will sustain the constellation, and it will add to this national capability.
Like its predecessors, TDRS-L carries the iconic look of two large parabolic antennas and a set of solar panels. Those antennas, each 15 feet in diameter, provided a bit of a challenge, since there is a limited amount of time they can stay folded and still unfurl to their proper shape. The processing teams kept close track of the time they were folded and had plans ready in case the antennas had to be opened if there was a lengthy launch delay. Identical to TDRS-K, which was launched in 2013, TDRS-L will take its station in geosynchronous orbit more than 22,300 miles above Earth. From there, it can basically hover over a point on Earth and communicate with every satellite and spacecraft below it, along with NASA's ground stations and other TDRS satellites. Working in conjunction with the 7 other operational TDRS platforms already in space, TDRS-L lets NASA stay in touch with its Earth-circling spacecraft at all times. In fact, TDRS spacecraft already in operation will help track this newest member of the family as it climbs from Cape Canaveral Air Force Station in Florida to its new home in space aboard an Atlas V rocket.
If you only had antennas in Africa, the middle of the Indian Ocean, and Australia, you generally are faced with certain coverage gaps. But looking down from the geostationary orbit of the TDRS constellation, you're able to seamlessly cover the entire period of a launch vehicle trajectory.
The United Launch Alliance Atlas V rocket that will power the 7,600-pound TDRS-L off the launch pad to its orbit location arrived at Cape Canaveral in October to begin a couple of months of processing.
Luckily, TDRS-L has been a very smooth flow. TDRS-K, which also was a smooth flow, but it was kind of the first time we had launched in about 10 years. A TDRS satellite, and it was now launching on a new vehicle that launched on a former Atlas. Now it's launching on an Atlas V. So we were able to apply a lot of the lessons learned that we went through the TDRS-K flow into TDRS-L.
The Atlas V, which includes the venerable Centaur upper stage, is relatively new to NASA's launch catalog, but has taken on the mantle of NASA's workhorse booster. In recent years, it sent probes to Jupiter, Mars, and the Moon.
Although it's reliable and has been very successful, we don't change the way we go into a launch campaign or into a mission. We have very strict requirements. So although we know it's very reliable and very successful, we don't diminish our involvement in any way, shape, or form. We're always give it the same level of rigor that we would do for any mission, whether it was the first or the 50th.
While the Atlas V is a newer booster, the Centaur is celebrating its 50th year in service. Developed at NASA's Glenn Research Center in Ohio, the Centaur was the first to use liquid hydrogen for fuel in a mix with liquid oxygen. Its success paved the way for later hydrogen-fueled engines, including those on the second and third stages of the Saturn V rocket and the Space Shuttle main engines. Launch day is January 23rd for the TDRS-L. For the launch team and those who build and process the spacecraft, it will be a testing time, which is normal for every launch day, no matter the mission.
So the last, 4 minutes when you're going to terminal count, it's just one after another. You don't have a whole lot of time. You don't have time to stop and start doing things, and troubleshooting. It's very intense.
I've been tremendously lucky to have a highly capable team. The United Launch Alliance and the Launch Services Program team is just exemplary. I couldn't ask for anything better. And in that regard, I like to make sure that the team as a whole is focused on launch day, that we're ready for the countdown, that we've done all the steps necessary leading up to launch day that will ensure a flawless execution and mission success.
We're now 46 minutes, 40 seconds into the flight of the Atlas V with TDRS-L. All of the data coming back through the TDRS-East tracking and data relay satellite indicates everything is going well while the vehicle is in a coast phase. The tracking station on the ground at Diego Garcia in the Indian Ocean has also acquired. They picked up about 10 minutes ago. So at this point we are having a nominal flight. We had rather exceptional weather tonight. It was very clear, the air was dry above, and it provided some rather exceptional launch coverage on our long-range trackers. So with the additional time with this long coast phase that we have tonight, we're going to run those launch replays once again. This is Atlas Launch Control, 1 hour, 32 minutes, 20 seconds into the flight of TDRS-L aboard the Atlas V. Right now, the coast phase is nearing completion. The status of the Centaur is good. The systems are stable, and very shortly it will be reorienting itself for the second burn. Right now, the data is coming through the Indian Ocean TDRS spacecraft and also from the Diego Garcia station in the Indian Ocean, and Guam has also acquired. So all of this being set up in anticipation of the second burn and TDRS-L spacecraft separation. And we're going to go back now and listen to Marty Malinowski because the Centaur is beginning some maneuvers in preparation for the Centaur second engine restart. The restart of the Centaur engines will occur about 6 minutes from now. Second burn of the Centaur will last about 1 minute and 3 seconds.
And about 5 minutes remain in this coast period before the second burn. Second burn is scheduled to be just over 1 minute in duration. Centaur continues to reorient to the MES 2 attitude and continues to roll at 1.8 degrees per second. And Centaur has begun to de-spin from its PTC.
Centaur restart will be at 1 hour, 40 minutes, 8 seconds. We're now at 1 hour, 36 minutes exactly. 37 minutes exactly.
Three minutes to MES 2. Centaur has achieved its MES 2 attitude and has completed the de-spin from the PTC.
Spacecraft separation will occur at 1 hour, 46 minutes.
Centaur has begun 4S settling to support the MES 2 start sequence with about 2 minutes remaining in this coast. And tank pressurization has begun, preparation for the MES 2 start sequence. Dual branch pressurization is underway. We have fuel pre-start. And we're seeing the first oxidizer flow control cycling with locks pre-start. We have Centaur ignition and full thrust on the RL-10. Chamber pressure looks good. Fuel ventura and LOX pump discharge are within band. Centaur PU is requesting a slight oxidizer-rich condition. Our RL-10 performance continues to look very good. Currently accelerating at 1.47 Gs. And we have MECO. Engine shutdown looks good. We have 4S settling motors on. Centaur has begun to reorient to spacecraft separation attitude. Fuel tank pressures have been vented down. They are stable currently. Centaur has begun 50% 4S settling. Prior to spacecraft separation, Centaur will spin the spacecraft up to 30 degrees per second to stabilize the spacecraft for separation. And Centaur has achieved separation attitude. Fuel tank pressures have been vented down and are stable. Quick check of the MECO orbit shows eccentricity is 4 balls 1, inclination minus 3 balls 4-2. Semi-major axis has a delta of 0.75 nautical miles. Those were all deltas from the nominal. Centaur has now begun the spin up in preparation for spacecraft SEP. Five degrees per second. Ten degrees per second. 15 degrees per second. Twenty degrees per second. 25 degrees per second. 30 degrees per second, and we have spacecraft separation. Centaur has begun its D-spin and is settling at 4S motors at the moment. And Centaur has completed the D-spin. Centaur will now continue on to its collision avoidance maneuver to inert the upper stage for the coast period. This concludes our broadcast of the TDRS-L AV-43 mission.
And this is Atlas Launch Control. Spacecraft separation has occurred, and we're standing by very shortly to get confirmation that the TDRS-L spacecraft has been acquired by the Dangara tracking station in Western Australia. And we will also have Tim Dunn, our NASA launch director, to come over and talk to us some about the countdown and then how the flight looks. And we have had first acquisition of the TDRS-L spacecraft through Dangara. So the spacecraft is now on its own and has phoned home. We're waiting to be joined here at the Public Affairs Console by Tim Dunn, who was our NASA launch director tonight. This is Atlas Launch Control, 1 hour, 50 minutes, 47 seconds into the mission of the TDRS-L. And joining us now here on console is Tim Dunn, who was our NASA launch director to this flight and the NASA launch manager during the countdown. And Tim, I wonder, first of all, give us a snapshot of how this looks like it's all turned out.
Well, thanks, George. Thanks for having me. And obviously, you showed some shots in the launch control room, and we're all thrilled. Successful spacecraft separation, and most importantly, a successful spacecraft acquisition by our ground telemetry. So we've confirmed that we've got a healthy spacecraft so far. So the launch team is thrilled, and as you can imagine, the TDRS-L spacecraft team is even more thrilled.
Well, take us back to the beginning of the count, and how did the countdown go, and then how did the flight look?
Well, it was just gorgeous weather on the Space Coast today, so it would have been a shame not to have gotten the launch off today. So we were blessed with tremendous weather. We have a wonderful rocket. We did not work any hardware anomalies on the Atlas V launch vehicle. Our spacecraft, the TDRS-L spacecraft, was rock solid, had zero problems with that. We were working, as we came into the count today, one lingering concern that popped up on the range yesterday with one range instrumentation site, and that being a radar that is needed to track the rocket as it flies out over the Atlantic. So the range team worked overnight and all through today to get us ready to enter countdown, and was able to bring that asset back online during the count for us to have and enable us to launch today.
And any further background on the short recycle that we had?
Oh yeah, so we get through the radar issue that we had. We had a nominal vehicle. Everything looked great. We're about ready to enter that final terminal count at T-4 and counting. And we began to notice just about a minute prior to that we were getting a little bit of noisy data coming back from our open loop spacecraft telemetry at the time. And turns out we were getting a few spacecraft dropouts. The spacecraft team needed a little bit more time. We decided to remain in the T-4 minute hold till we better understood that. Turned out it was a situation with multipathing with the open loop RF transmissions between the antenna located at TEL-4 and the Atlas V vehicle. And so once that situation was well understood, we did discuss that on our Anomaly net per our process, and we decided that we would, instead of staying open loop for the next attempt, we would stay on our ground line telemetry, a hard line. Obviously that was very clean data, and we made the switch to the open loop RF at T0 or at liftoff. So that was a great plan that the team came up with, and we executed that plan and got back into the countdown, established a new T0 at 33 minutes past the hour, and were able to execute that and had a beautiful liftoff.
Well, Tim, this is just the start of a very busy year for launch services program, so outline some of the missions we've got still coming up. I know Vern mentioned some of them, but it's we've got a lot of missions coming.
Well, it is an exciting year for launch services program, this being our first. We look to go to the West Coast for a couple of Delta II missions this year. We have the OCO-2 mission that's going to launch on a Delta II from Vandenberg Air Force Base, Space Launch Complex 2. That happens this summer in July. And then in the fall, in November, we go back out to Vandenberg for another Delta II mission, the SMAP mission. And so we're excited to launch on Delta II again. It'll be about 2.5 years since our last Delta II launch. We also have another Atlas V mission that's currently manifested for later in the year, the MMS mission on the East Coast. So we've got a full slate of science missions ahead of us, and everyone in LSP is just thrilled with the TDRS-L launch today.
Well, Tim, thanks very much, and this has certainly been a happy moment for the TDRS team, because they're now 100% on the two they've got now on orbit for for their program, and maybe another one coming downstream a ways, but the two that they wanted right now, they've got right now.
Very good. And if I could, George, I know you mentioned it during the countdown, but this launch was dedicated to Skip Mackey, Memorial Launch.